Well, hey, fancy meeting you here. Okay, so the next thing we need to talk about, yesterday we talked about how to solve for unknown lengths using the three primary trigonometric ratios. Okay, now today's the same thing, except instead of solving for unknown lengths, we're going to look at how would I figure out the angle if I knew what the two pieces of my ratio were. For instance, you know that sine is opposite over adjacent, right? Well, if you knew the opposite of a particular angle and you knew, sorry, I said sine was opposite over adjacent. Sine is opposite over hypotenuse. I wasn't paying attention to myself. If you knew the opposite and you knew the hypotenuse, but you didn't know the angle that was associated with those two lengths, could I go the other way and figure out the angle? And of course, the answer is yes, I can. Everything we do in math is bidirectional. If I can go one way, I can go the other way. So if I have tables stored in my calculator that allow me to input an angle and they'll give me out a ratio, then I probably also have tables stored in my calculator that if I could give my calculator the ratio, they will tell me the angle associated with that ratio. Okay, and that's what we're going to explore today. So the word inverse. Inverse means an operation that undoes another operation. So for instance, division is the inverse of multiplication because it undoes the operation. So far, we have always been given an angle and asked to solve for a missing length. If we have two lengths, though, we can also head in the other direction and figure out the angle that goes with the ratio. To do this, we take the inverse of the trigonometric ratio. Now, for the most part, if your calculators are set up well, and if you have a graphing calculator, it's totally set up well, for the most part, inverse operations are often found as the second function of the regular one. So if you take a look at sine, your sine button there, and you just look right up above the button, it's probably going to say sine to the -1. And if you look at cos, right above that, we'll say cos to the -1. So those are the inverse, okay? So you get them by, on a Casio, you just press shift sign, and on a TI, you press second function sign or whatever, okay? And that will get you the inverse operation. So here's what it's going to look like. For example, if we knew that the sine of an angle had a ratio of 1/2, we would arc sine. Now, arc sine is the official term that I would like you to use, but you'll often hear it called, we would inverse sine or take the sine inverse. So that's acceptable as well, but arc sine is the better word there. This ratio and get an angle of 30 degrees. Now, mathematically, this is essentially what we're doing. We start it, remember I said that every question starts the same way. So that first line you see is still saying the exact same starting point that happened with every question we did in the last lesson. Sine of theta equals the ratio. Sine of theta equals 1/2 in this instance. Now, what we did is we arc signed both sides, okay? So when I take the arc sine of this guy, it undoes the sine ratio and I'm left with theta, okay? Then on the other side, I'm left with the arc sine of 1/2. That is just something I stick in my calculator, the arc sine of 1/2. So I'll go second function sine of 1/2, and then that'll give me 30 degrees. Again, make sure your calculator is in degree mode. I assume it is, but something you should always check. The other thing is, depending on how old your calculator is, it's good when you're dealing with fractions to actually use your fraction button. So on a Casio, use the S to, or the fraction button. It might say ABC. It might go like that, or it might look like this, okay? But essentially on a Casio graphing calculator, it's right above the number 7. On a TI, if you want to open up a fraction like that, you'd go alpha y equals 1, okay? If you can't do that because you have an older model of those units, that's totally fine. You just have to remember that when you go arc sine, make sure it has an open set of brackets there, and then go 1 divided by 2 and close your brackets, okay? So make sure you can do that and get at a conclusion of 30 degrees. Okay, so we're just going to practice that for a couple of examples here. So cos of theta equals 0.7880. So this time it's not a fraction, but doesn't matter. That still represents the ratio of cos. Now remember, cos is adjacent over hypotenuse. So this is saying that for some particular angle, the ratio of the adjacent divided by the hypotenuse must give me 0.7880. So now we're going to say, okay, I want to use my calculator to figure out the angle that's associated with that ratio. So I'm just going to go arc cos to the -1 of 0.7880. So I'm arc cosing both sides. That leaves me with theta on the left and 38 degrees on the right. Okay. Tan of theta equals 2.0503. Again, I will arc tan both sides. That will leave me with tan on the left, and that will leave me with 64 degrees on the right. Okay. I assume you're pausing me to do this yourself before you see the answer. Okay. And then we have sine of theta equals 0.6157. I will arc sine both sides. That's going to leave me with theta on the left, and then the arc sine of 0.6157 should give you 38 degrees. Okay. Finally, we have cos theta equals 0.6978. I will arc cos both sides. That will leave me with theta on the left and 46 degrees on the right. Okay, so calculate the angle to the nearest degree. So now I'm back into a triangle. I need to take stock of what I have and what I need. Okay, so given that this is the angle I'm looking at because it's marked as theta, this is my opposite, this is my adjacent, and this is my hypotenuse. So I don't have the angle, but I do have the adjacent and I do have the hypotenuse. So which trigonometric function uses adjacent and hypotenuse at the same time? That's cos. So I'll say cos of theta equals 5.3 over 17.9. Then I will arc cos both sides. Okay, I would like to see this in your work because it's good mathematical communication. That leaves me with theta on the left and then 72.777 on the right. Now, we were asked to round to the nearest degree, so my final answer will be 73 degrees. Don't forget, this is really important because a lot of your answers in this section will be the degree. You have to have that little degree symbol there. If you don't, it's just like you have improper units or you forgot your units and you'd get docked off half a point. That little degree symbol is super important because if you don't have that degree symbol, you're actually referring to radian measures, and that's a whole other ballpark. Okay. So, oh, let me get that ink off for you. So here is theta that I'm looking for. And given that theta, this is opposite, this is adjacent, this is hypotenuse. So I have the opposite, I have the adjacent. So which trigonometric function uses opposite and adjacent? That would be tan. So I'll go tan of theta equals 15.1 over 10.4. I will arc tan both sides. And then theta will be 55.443. Again, I was asked to round to the nearest degree, which is the nearest whole number, so 55 degrees. Okay, always, always, always make sure you read the question carefully and you're following exact rounding directions. Okay. All right, given this guy, now this arrow refers to angle A, and that's what I'd be looking for here. So this guy here is my opposite, this guy here is my hypotenuse, and then this guy would be my adjacent. So I have the opposite and I have the hypotenuse. Which trigonometric function uses opposite and hypotenuse together? That would be sine. So I'll say sine of A equals 175 over 340. I will arc sine both sides, and that will leave me with A, or theta, equals 30.9778. Rounded to the nearest degree would be 31 degrees. Okay, don't forget your little degree symbol. Okay, so this guy, again, I'm looking for that little arrow section, so that's my B here. So given that that's B, this would be my opposite, this would be my hypotenuse, and this would be my adjacent. So I'm looking for, I have the adjacent and I have the opposite. Which trigonometric function pairs up adjacent and hypotenuse? That would be cosine. So I'll say cos of theta equals 135 over 200. And then I will arc cos both sides, and that will leave me with theta equals 47.5458, rounding to the nearest degree, 48 degrees. Okay, now we'll do a couple application questions here. The string of a kite is 105 meters long. The string is anchored to the ground and the kite is 90 meters high. So what I did was I drew a kite, and then here's the string. Because it's anchored to the ground somewhere over here, that's what makes this hypotenuse. The string is actually the hypotenuse here, okay? And then I know that the height of the kite is 90 meters, so I stuck that there. Determine the angle formed by the string and the ground. So here's the ground, here's the string. So I marked theta as the angle formed by the string and the ground. And now I'm gonna solve. Well, what am I looking for? This is opposite, this is adjacent, and this is hypotenuse. I have the opposite and the hypotenuse, so I want to solve this using the trigonometric function that uses opposite and hypotenuse at the same time. That is sine. So I'll say sine of theta is 90 over 105, and I will arc sine both sides, and that will leave me with theta equals 59 degrees. So the angle formed by the string and the ground is 59 degrees. Okay, a support cable. By the way, when you're doing different questions in your textbook and stuff, support cables are often called guy wires, G-U-Y. Just if you're thinking, what the heck is that? It's just some sort of cable that's supporting it. A support cable is anchored to the ground 5 meters from the base of a telephone pole. The cable is 19 meters long. It is attached near the top of the pole. What angle to the nearest degree does the cable make with the ground? So I want you to pause me and draw your own picture. Your picture should look something like this. It may be kind of the mirror image of that, that's fine. So I knew I was anchored 5 meters away from the base, so that was my horizontal, and I knew that the cable itself was 19 meters. I'm asked for the angle that it forms with the ground, so I'm looking at that guy. Then I'm gonna figure out what do I have and what do I need. I need the angle. Given that angle, this is my opposite, this is my hypotenuse, and this is my adjacent. So I'm looking at pairing up adjacent and hypotenuse. The trigonometric function that does that is cosine. So I have cosine of theta equals 5 over 19. And now I'll arc cos both sides. That will leave me with theta equals 74.74. And then when rounded, it asks to the nearest degree. So that'd be 75 degrees in my conclusion. Okay. All right. Tell me what the sine of 90 and the cos of 90 is. So you should have gotten sine of 90 is 1 and cos of 90 is 0. Now, explain why using a diagram. So I'm going to take some time to develop this with you. What I'm going to do is I'm going to start with a triangle like this. Okay, and we're going to play with sine for a second. So I'm going to mark that as theta. And let's say that I've got, well, I don't know, let's say this is 3 and this is 5. Okay, and so right now, the sine of theta would be 3 over 5. Okay. Now, what happens if I start making the adjacent here shorter? Okay, I'm gonna leave this as 3, but I'm gonna make this shorter. And so you might see that and say, I'm just gonna get a different color here so you can see. So let's say now my triangle looks like this, and now that's theta. Okay. So a couple things I want you to notice. The opposite didn't change, but the adjacent would have changed, and actually the length of the hypotenuse would have changed as well, okay? So the adjacent got shorter. What would have happened to the hypotenuse? Take a look at the lengths of these hypotenuses, okay? Is the green hypotenuse longer or shorter than the purple hypotenuse? And the answer to that is it's shorter. So let's say for this guy, maybe it turned out to be 4. So I say sine of theta equals 3 over 4. And now let's do it again. Let's shorten the adjacent to form this triangle here, okay? And now, again, that hypotenuse has gotten shorter, okay? The opposite has not changed. I've kept that height the same, okay? And so I might be looking at sine of theta equals 3 over maybe 3.5 or something like that, okay? 3 over 3.5. Now, what's happening? Well, the first thing I want you to see is theta, theta, theta. As I keep coming in here, my thetas are getting larger, okay? This theta is bigger than this theta. This theta is a larger angle than these thetas, okay? So I'm getting bigger and bigger and bigger. Now, actually, I'm approaching 90 degrees, okay? And what's happening to the ratios? Well, 3 over 5 is 0.6. 3 over 4 is 0.75. 3 over 3.5 is 0.86. Okay, and so what I want you to notice is as I keep going up, these guys are actually approaching a particular number. And here's the number that they're approaching. Everything falls apart when this becomes nothing. Okay, when this becomes nothing, now a triangle doesn't form, right? The triangle itself falls apart. But essentially what happens is my height and my hypotenuse are the exact same. And so I'd get 3 over 3, which is 1. And that happens when theta actually hits 90 degrees, okay? So when theta becomes 90 degrees, the triangle kind of falls apart, and I'm left with essentially a adjacent, let's actually start with the opposite. Opposite was 3, hypotenuse was 3, and adjacent is 0 when I hit that 90 degrees, okay? So this now explains why the sine of 90, which is opposite over hypotenuse, 3 over 3 is going to give me 1. And this whole explanation is the same explanation to say why the cos of 90 is 0, because the adjacent, when I hit that 90 degrees, the adjacent is 0. 0 divided by the hypotenuse, 0 divided by anything, is 0. Okay? So that's the diagram that I want you kind of comfortable with. Now, there is this link. You do have to have Flash in order for it to work, but there is a link from your textbook that kind of does this interactively if you'd like to check that out as well. So what can you say about the sine and cosine ratios? What I want you to understand at this stage of the game is sine and cosine can never be greater than 1. Now, the reason for that is partly you can think about it from this diagram, and partly you can think about it for the fact that both ratios of sine and cosine are a side of the triangle divided by the hypotenuse. Well, by definition, the hypotenuse has to be the largest side of the triangle. And so there's no way, if I'm looking at a fraction where the larger number's on the bottom, there's no way to get that bigger than 1, okay? So super important that you realize sine and cosine can never be greater than 1. And the reason is because the hypotenuse is always the larger side of the triangle, and the hypotenuse is always on the bottom of those two fractions. Now, for tan, that's not the case. Tan is opposite over adjacent, so I actually can have tan ratios that are larger than 1, but not for sine and cosine, okay? So that's it for this guy. Tomorrow, we're going to take this just a wee bit deeper, not much, and we're going to look at just a few more vocabulary words that we have to deal with as we go into further applications of some of these guys, okay? In the meantime, do lots of practice and make sure you connect with me if you have any questions. Take care, guys. Bye-bye.